Right, so in this video we are going to show an application of the linear impulse momentum equation and combined with angular impulse momentum equation in the context of the motion of a rigid body. And we will take a variation of the problem and we will show a certain subtlety of the problem as we move forward. So the problem goes as follows. So it is given that there is a uniform stick that is resting on a horizontal surface. Assume that it is just held in equilibrium. It is of mass m and length L, and at the bottom of the bar there is an impulsive force that is applied. So this F hat represents an impulsive force, and as a result of this, the bottom of the bar gets an instantaneous velocity V0. Okay, so it gets an instantaneous velocity V0 as a result of that impulsive force or a strike. So we want to find out, so determine the angular velocity of bar immediately after the impulse, and we also want to find the velocity of the center of mass. Immediately after impulse. Okay, so these are the two quantities that we are interested to find. So the way we proceed is, firstly, let us say that this direction from left to right, perpendicular to the ground, or parallel to the ground, is x, and let's say this is the geometric center and the center of mass. So let's call that C, and it is of course going to be at a distance of L/2 from the two ends. And furthermore, let's say that the angular displacement of the bar from the vertical is given by the angle theta. So theta dot is then the angular velocity, and we are interested to find out the initial angular velocity that is produced by this impulse and the initial linear velocity of the center of mass that is produced as a result of this impulse. So let us say that velocity of the center is given by Vc. Okay, and so we will denote, so therefore find theta dot 0 and Vc 0. Okay, 0 meaning it's the instantaneous velocity, it's the velocity right after the application of the impulse. All right. We can also assume that the friction, the surface is frictionless, although that is probably not of much significance here, because we are not interested in finding out the effect of friction on this. The effect of friction will only occur once the motion has started. So probably the effect of friction for this particular problem is not relevant, Instead, our interest is in finding the instantaneous angular velocity and Vc right after the impulse has been applied. Okay, so the linear impulse momentum equation for a rigid body or for a particle, basically, that, I mean, if you draw the free body diagram of this, here is the gravitational force, then you have the normal reaction. Remember that the motion that we are interested in is at theta equals 0, and there is an impulsive force here. Yeah, I think it is safe to say that we are not considering friction in this. I don't want to claim at this juncture that the friction will not have any effect without analyzing that aspect. So let us just say that this is a case where there is no friction between this end of the bar and the ground at the instant of application of this impulse. So these are then the three forces. Of course, F hat is not a force, it is F hat delta t, which is the force. F hat is the impulse. So F hat times delta t, where delta t is the infinitesimally small duration over which this impulse acts. Alright, so this is the free body diagram, and then we can say that from linear impulse momentum equation, we have F hat is equal to, let's say this velocity is, this direction is x, and we are going to consider the velocity that is produced as Vc0 and the angular velocity that is produced as theta dot 0. Okay, so F hat is equal to m times Vc0. All right, so this is basically the initial momentum of the center of mass. C in the x direction was 0, so the final momentum is mvc0, and so that's the change in momentum, and that is caused by the impulse. So this is our equation 1. Now from angular impulse momentum, equation, we have IC. IC represents the moment of inertia of the bar about the center of mass, times theta dot 0 is equal to the net angular impulse that is applied. So you can see that mg and n are not going to provide any angular impulse, because let me just think about one thing. I think this one should be, just trying to think about the units here, mass times kg meter per second, and this is Newton, so kg meter per second squared. So this times delta t. Okay, yeah, the units are good. So in this case, the angular impulse is going to be not due to mg and n, because they are not causing any torques or any impulses about the point C, but rather it is this f prime, or rather f hat. So f hat times L by 2, and you can see that that impulse is going to be a positive impulse, angular impulse, because it is going to try to increase the value of angular velocity. The initial angular velocity was 0, so the change in angular impulse is IC theta dot 0 minus 0. So this is our second equation, right? Now we know that as a result of this impulse, the bottom of the stick gets a velocity v naught, right? So this is because of this impulse, the bottom of the stick gets a velocity v naught. So therefore we can also say that the rotation that is being produced by this impulse is v naught minus vc naught divided by L by 2 in the counterclockwise direction. Therefore theta dot 0 can also be represented as v naught minus vc naught divided by L by 2, right? We know the velocities of 2 points on the rigid body, and so we know that if the velocities are parallel to each other, then the difference of the velocity divided by the perpendicular distance gives us the angular velocity. So this is our third equation. Okay, but this expression is not yet the expression that we are looking for, because we don't know the value of vc naught. So you can see here that there are three unknowns: f prime, vc naught, and theta dot naught. So we need to just eliminate f hat, rather, not f prime, and find the value of vc naught and theta dot naught. So from 1 and 2 we have you can see that IC is 1/12 ml squared, theta dot naught is equal to, now f hat is equal to m vc naught times L over 2, right? So we can cancel m from both sides, and we can cancel 1 L from both sides, and we have theta dot naught is equal to six times vc naught divided by L, right? So that's our expression for theta dot naught. Now we can substitute this here. So therefore from 3 we have 6 times vc naught over L is equal to, from 3 we can just write this as 2 times v naught minus vc naught divided by L. So we cancel L from both sides, and we have 8 times vc naught is equal to 2 times v naught, which means that vc naught is equal to 1/4 of v naught. So we actually have the velocity of the center of mass. We see that the velocity of the center of mass as a result of this impulse is 1/4 of the velocity of the bottom. Now from here, now we can calculate theta dot naught. So theta dot naught then is equal to 6 times vc naught divided by L. So 6 times 1/4 v naught divided by L is what we have. So that is going to be 1.5 v naught over L. Right? So that's our answer. That is what we have been looking for. The angular velocity and the velocity of the center of mass right after the impulse. Now here what we have done is we have applied the angular impulse momentum equation. It's not a conservation equation, it's the angular impulse momentum equation and the linear impulse momentum equation. And they basically say in the linear case that the impulse is equal to the change in momentum, and in the angular case it is the angular impulse is equal to the change in the angular momentum. Right? Now let us do a little bit of an analysis of the results here to see if everything makes sense and to get an insight into the kinematics or the dynamics here. So essentially the answer that we got is Vc naught is equal to 1/4 V naught, and theta dot naught is equal to 1.5 V naught over L. All right. Now let us see one thing. You see that the bottom has a velocity of V naught, right? That is as a result of this impulse. The center has a velocity of 1/4 of V naught, right? So at the top, let's call that velocity Vt, and I'm deliberately showing in the other direction, but because as you will see, indeed the velocity at the top is going to be in the reverse direction. And basically the way to find the velocity at the top is basically to draw a triangle and use similar triangles, because these two points are equidistant from the center. This is the center C, so therefore we can say that theta dot naught is equal to 1/4 V naught minus Vt divided by L over 2, and that is equal to V naught minus 1/4 V naught divided by L over 2. In other words, there is a linear variation of this velocity as we go from the top to the bottom of the bar. The velocity is linearly varying, and so if I cancel this L by 2 from both sides, what I get is that this is 3/4, so I get Vt is equal to 3/4 of V naught minus 1/4 of V naught, so that is half of V naught, right? So you can see here that when I apply the velocity, when I apply this impulse which causes the bottom of the bar to get an instantaneous velocity of V naught, the top of the bar is getting an instantaneous reverse velocity of V naught over 2, right? Now you may be wondering, I applied a force or an impulse over here, how did this impulse get translated? I did not apply any impulse here, but how did it get translated? Well, that is because we are dealing with a rigid body here. What happens is that when we apply an impulse here, let's say it is f hat, if you break this bar down into elements, then over here, if you sketched the free body diagram of just this element, at the bottom you have f hat, and at the top you would have a f hat 1 reverse, in the reverse direction, and that is because there are two elemental masses, and this f hat gets transmitted to this element, and it transmits to the next element, but the next element gives an equal and opposite impulse. So the next element then has an equal and opposite f hat 1, and then the same thing happens at its top. It gets a f hat 2, and so for each of these elements you can see that the result of this impulse at the bottom is that there are internal action-reaction impulses that are generated, and they travel to the top. And at the top, what you have is the following. At the top is there is going to be a forward-going impulse, let's say that is f hat n. If there were n different elements that were being created, and that impulse, well, it can be in the forward direction or it can be in the backward direction, depends on how the impulse gets distributed along the span of the bar, and that impulse causes the velocity at the top. And in this case, we didn't have to do this finite elements, but we can predict from the variation of these forces, of these impulses, that the velocity at the top, Vt, is going to be half of v by 2. So that is how the impulse is getting transmitted from the bottom to the top. It is happening because each of these elements have got a mass dm. Okay, that is why when there is a mass, when the mass is distributed, then it can absorb the forces and it can produce a velocity, a finite velocity. Okay, and that is how the impulse gets transmitted from the bottom to the top. Now, an alternate version of this problem is what would happen if we took a similar scenario, but instead of a distributed mass, that is a bar, we took the same mass, but it was distributed among two lumped masses. So the length is still L. Okay, so we have two lumped masses. Okay, and this is a massless rigid rod. So it's the same scenario, with the exception that we have a massless rigid rod that connects the two lumped masses. The overall mass and the length are the same, and let's say this is the ground, and we apply an impulse at the ground and it produces an instantaneous velocity v0 of the bottom mass. Okay, so same thing happening. The difference is that the mass is now lumped at the two extreme endpoints. The center of mass is still at L over 2, and so let's say it produces a velocity vc and it produces an angular velocity theta dot. So same thing here, and let's see if our results are going to be the same or if they are going to be different. So we still have f hat is equal to m times vc naught. Right, so let me just check if this equation, yes, so we still have this equation. Let's call it equation 1, and we still have the rotational equation, which is IC times theta dot naught, which is the change in the angular momentum, is equal to the angular impulse, so that is f hat times L over 2. That equation remains the same. In addition, we also have the angular velocity determined by v0 minus vc naught, okay, divided by L over 2 is equal to theta dot naught. So you see, structurally the three equations are exactly the same. Now let us process the equations 1 and 2. IC is going to be the net moment of inertia due to these two lumped masses about the center. So this one is going to be m over 2 L by 2 squared. So you have m over 2 L by 2 squared, and this is going to be again m over 2 L by 2 squared. So this is the net moment of inertia of this dumbbell kind of situation about the point C, times theta dot naught is equal to f hat times L over 2. So I'm going to substitute m vc naught L over 2. All right, so this is from 1 and 2. Now you see that this expression, what does it become? It becomes m times L over 2 whole squared when you add these two terms up. So it's going to be m times L squared divided by 4 times theta dot naught is equal to m Vc naught L over 2. So I'm going to cancel the m, I'm going to cancel one of the L's, and I'm going to have, let me try to get the equation in a similar form. So I have theta dot naught is equal to Vc naught times 2 divided by L, right? And so then what we are going to do is we are going to substitute this. So from 3, then we have V naught minus Vc naught divided by L by 2 is equal to Vc naught times 2 divided by L. So I'm going to cancel L from the two sides, and 2 is then going to go to the numerator, and so we are going to have 2 V naught is equal to 4 Vc naught. In other words, Vc naught becomes equal to half of V naught. Okay, and therefore theta dot naught becomes equal to, from here, V naught divided by L. And these answers are different. Let us compare these with the results that we got. Let me just put them. See. Yeah. So you see here, these were the original results. When we had a uniform bar, the velocity of the center was 1/4 V naught. When we have a dumbbell, then the velocity of the center is half of V naught. Right? When we had a uniform bar, the angular velocity that the rod achieved immediately after the impulse was 1.5 V naught over L. Okay? When we have a dumbbell, the angular velocity achieved is V naught over L. So the answers are different. And the answers are different because of the fact that in this case what happens is that because this is massless, the impulse that is applied here cannot travel through these through elements here to this mass. Why? Because if there was an impulse that was traveling through these massless, to this massless rigid rod, then that impulse would create an infinite velocity of this massless rigid rod. Why? Because we have considered the rigid rod to be massless. So if the rigid rod is massless, a non-zero impulse is going to cause an infinite velocity, which is going to be break the integrity of this rigid body. So in consistent with the physics of the rigid body, we see that indeed the physics works out in such a way that there is no impulse transmitted to the upper mass, and this can be verified. You can see here that indeed in this case the velocity of the top, so let's say here the velocity is V naught. At the center we said the velocity is V naught over 2. Let's say that the velocity over here is V top. Then we have theta dot naught is equal, I mean you can already see that it's going to be 0 because these are equidistant. So if it drops from V naught to V naught over 2 by half the distance, it's going to drop to 0 at the top. But let's just work out the math. It is V naught over 2 minus Vt divided by L over 2 is equal to V naught minus V naught over 2 divided by L over 2. So we can cancel these two L over 2's, and we have Vt is equal to V naught minus V naught over 2 minus V naught over 2, which is equal to 0. So indeed we get the velocity of the top to be at the top to be equal to 0. So we see that when instead of a uniform bar, when we consider two particles that are connected by a massless rigid rod, then the velocity of the top is equal to 0. It does not feel any effect of the impulse. Why? Because the impulse cannot travel through this massless rigid rod. Okay, so that's why it sees an initial velocity of 0. Now what will happen is, if you allowed the motion to resume after the impulse, then there is going to be, because of the tension in the rod, it's going to cause the motion, it's going to cause a motion in this particle eventually, but it's not going to happen instantaneously when the impulse is applied. In contrast, when we considered the rigid body, we found out that at the instant when the impulse is applied here, the top does get a velocity, a linear velocity, or rather a horizontal velocity parallel to this bottom, and that is because that the mass is uniformly distributed, or there is a distribution of mass which allows action reaction impulses to travel to the top and produce a velocity at the top. All right, so that is what I wanted to show through this problem. Rather simple problem, but there is a very interesting observation that can be made here, as you could see, and we showed how the solution is going to be different based on whether you consider a rigid body, that is a bar with mass distribution, versus two particles connected by a rigid massless object. So that is what I had. This is a nice simple application of the combination of the linear impulse momentum equation and the angular impulse momentum equation. Alright, so that is what I have for this video. Thank you.